You have problems though, because what the electrodes are picking up is an amalgamation of millions of neurons, the output of millions of decision making, and you get averaging turning up, and completely different thoughts can spark the same neurons. The neurons are used for different thoughts and different ideas. The American military have tried to use electrodes of this type to give their fighter pilots a high speed of response. So when the pilot at the moment wants to fire a missile, he would have to go through all a long time of thinking about it, pressing a button, the missile fires. That all takes time. If he can just think about it and the missile fires, that's better. So the pilot learns to think about it in a certain way and the missile fires. The trouble is he then thinks about going home and having a glass of beer and the missile fires because the same neurons are doing something very different. So it's not really something that can be used for a fail-safe device. And so you may see that occasionally on the news they have somebody in some university where they're wearing a hat like this because it looks quite cool for the BBC, and they're in a little buggy, and it moves to the left and then it moves to the right. And then it goes to the left when it should go to the right, but it doesn't matter so much because it's a bit of fun in the lab, and that's all right. So there are potential uses of this, but it's quite limited. Now let's go to something that is commercially available and very, very useful. What you're going to see is a guy who has Parkinson's disease, very debilitating disease. He has received electrodes right in the central area of his brain, in the subthalamic nucleus, right, a tiny part in the center of the brain. Now, you may have wondered about this. You'll see the assistant switch on the power packs, and the power packs are actually positioned here. Now, you probably find, like I have, we have evolved, and all the parts of our body have uses, and they do things. And here, there's a lot of space. It doesn't seem to do a lot. Well, this is actually 4 pieces of technology to be implanted. It's a wonderful sense of evolution. And that's what you'll see here. The assistants will switch on the power packs that are positioned here, all fully implanted. There are then wires going up subdermally, underneath the skin, into the electrodes deep in the person's brain. And you'll see how the person is with purely electronic stimulation of their brain. So this is a genuine person with Parkinson's disease, and what you'll see is when the power packs are not switched on, how they are with the disease, and then how they are when the stimulation's operating.
I'd like to show you in 2 minutes what was the status of Mr. Plessman when he was referred to us by his neurologist in Belgium. And you see him before surgery, without drug, unable to stand up by himself. He's helped by Patricia Limousin, who is a neurologist in our group, and he's not able to do anything of, as he will tell you, makes your life looking like normal. He's not able to walk. He has having dystonia, which are muscular contraction, deforming the different joints, and this is the best he could do without the drugs, with the help of people around him and mainly his wife and friends. He was referred because the drugs were not working anymore. He was not having any more improvement, and as he will tell you, he was just stuck to a wheelchair. This is after surgery. You see the tremor. We turn one of the 2 stimulators which were implanted with electrode into his subthalamic nucleus, which is a tiny part of the brain, and you see that in a few seconds the stimulation induces a stop of the tremor. This is still visible on the other side. We will turn on the stimulator on the right side, and you will see something even more spectacular than that. You will see that the patient feels again free, and he reset himself in his chair in the position where he feels the most important. He will obey Dr. Pollack in doing some tests, even if he feels that those tests are a little bit useless as compared to the feeling he has. We can do that almost normally. On the right side, should I do it longer? Does he say? And he'll show it on the other side. and then he will walk, he stood up alone, he is without any drug, you see him walking, turning. It was a few days before the Vienna meeting on movement disorder.
This stimulator is very successful. There are thousands of people that have that. We work with a surgeon, Tipu Aziz, at the John Radcliffe Hospital, Oxford. He puts in one of these every week in a new patient. So, and that's just one hospital. There are about 7, I think, hospitals in the UK that you carry out this operation. So it gives you an idea, even in the UK, the number of people that are benefiting from this technology. One problem with it is that it actually provides a current all the time. It's stimulating all the time, and it uses up a lot of power. So after 18 months to 2 years, the patient has to go back into hospital, have the power packs replaced, have a new power pack put in, and off they go. And you can get potential problems due to infection with any operation. You can have problems like that. And then 18 months, 2 years later, they have to go back in again. So it's a bit traumatic, and it's not something that is perfect by any means. But the stimulation is great. The person will leave it on all the time. They'll sleep with it on, because they can sleep. With Parkinson's disease, it's really a problem. That guy drives his car around, he leads a normal life because he has this stimulator, electronic signals. He doesn't take any pharmaceuticals, any chemicals to counteract the Parkinson's disease. It's just this electronic stimulation. But what we're trying to do with Tipu is to make this stimulator a little bit more intelligent, so it only stimulates when it needs to stimulate. So it doesn't stimulate all the time, it just stimulates when tremors are about to start, or when the dystonia, the muscle locking, is about to start. But it needs to know when that's going to happen, so it stimulates so that it doesn't actually happen. Hopefully you don't grumble at me showing some diagrams. So this are actually signals from an actual patient. The bottom one is EMG. This is, I'll move that in case that's getting away. This is muscular signals. This is from the tremors. So there's nothing much happening, and then we see here, this is where the tremors start. So this is giving us a mechanical indication, a movement that the tremors are underway. This one, the same patient, the same time sequence, is the electrical activity deep in the person's brain at exactly the same time. This is in the subthalamic nucleus, local field potential. So this is electrically what's going on. We can measure via the electrodes deep in the person's brain at the same time that this happens. You can get an idea here. It's very difficult, but the variation of the signals is more here. When the tremors start, it doesn't seem to vary so much, but other than that, we can't pick up much from it. What we've done is to train an artificial intelligence system, an artificial neural network, a computer, to just monitor this electrical data. So the input to our artificial intelligence system is this electrical activity. And what we want our artificial intelligence system to do is 2 things. One is to indicate when there are tremors, more to confirm it knows what it's doing, but most of all to predict accurately when there are going to be tremors before they actually occur. And this is the output from our artificial neural network, our computer artificial intelligence system. We see here, 45, 50 seconds, the output goes high. The network is indicating tremors are actually happening. Remember, it's just sitting looking at the electrical activity in the person's brain, but it's indicating there are tremors on the outside from the electrical activity. Here, which is a bit more important, 14, 19 seconds, we get a couple of spikes. Something's going on, our network tells us. And in fact, if we look down here, and maybe even at the move, it's as though the tremors are starting, but they don't get going. And our network picks up on that. Something's going on. This is the key one. 30 seconds, big spike, something is